Hello everyone, welcome to a brief introduction of a computer program and member hunter. My name is Jakub Heifler. I work at the Department of Geological Sciences at Masaryk University in Brno, in Czech Republic, and I'm an author of the program. A member hunter may be of interest to those who need to assign a member formulae to minerals from their empirical formulae, in particular to the minerals with complex mixing behavior involving both the heterovalent and homovalent substitutions. The Commission on New Minerals, Nomenclature and Classification of the International Mineralogical Association approved a so-called dominant valency rule, which will be followed. Guidelines on how to apply the rule are described in a publication by Bossi et al., published in the Mineralogical Magazine in 2019. An alternative approach, the dominant n-member rule, results in an n-member formula as well, which may often be the same as that obtained from the dominant valency rule, but may also differ. The member hunter outputs results from both approaches, allowing for comparison. Deriving the n-member formula manually using any of the two approaches may be challenging, and these are situations when a member hunter can be helpful. What follows is a tutorial of how to use the program. I use a titanium-rich garnet from MagnetCAF as a working example, which was also used by Bossi et al. To demonstrate the dominant valency rule approach. So let's start with the program description. A member hunter is a free standalone application coded in MATLAB. MATLAB license is not required for running the program. However, what you need is a MATLAB runtime, a collection of shared libraries. This is free of charge. You can download it either from MathWorks website or together with nMember Hunter. Please watch the instructions in the program documentation. When nMember Hunter and the necessary MATLAB runtime libraries are installed on your PC, you can launch the nMember Hunter execution file. At first, you are prompted to start a new project or load an existing one. We start with a new project for now. The program, such as creating a folder nMember Hunter projects in your Documents folder on your C drive if it doesn't exist. The easiest way is to accept this suggestion. This dialog only refers to the recreation of the new folder, not where your project will be stored. If you don't wish to create the folder for any reason, you can select No. If you choose No, please watch the documentation, otherwise this dialog will appear during every future run. I agree, so I select Yes. Then the program needs to know where your project will be stored on your PC. There is a suggested default starting path, which is either EMH project folder or it depends on your personal settings. Here you specify or confirm the target path for every single new project. Given that I expect to develop many future projects, each of them generating several files, I decided to create an additional lower hierarchy folder in my EMH project folder. Please don't save your projects in a protected folder such as program files. After this step, input a name for your project. So I write Garnet or MagnetCAF, for example, and confirm. Subsequently, main window of the program appears. The functions are launched and controlled from this graphical user interface. In general, we proceed from the top boxes to the bottom. Since the project information has already been defined, we will now continue with the Garnet formula constraints. We add the sites as needed using the yellow button. We need 3 cationic sites and 1 site for anions. Don't forget to fill in the stoichiometric coefficients for each site. Use all site buttons to define additional site specifics. You can modify the site name, so we can change the site 1 to X, for example. Major importance are definitions of the valences and constituents involved at the site of interest. To add divalent cations at the X site, select +2 to the bottom and then select the involved constituents from the periodic table of elements. The note, there are tips or instructions attached to some user interface elements. So just aim the cursor at them to display them. Once all the mineral formula constraints are completed, click on the Create Database button. This function develops a complete database of all site total charge arrangements, root charge arrangements, and charge balance formulae relevant for the set of constraints of interest. I hope this function can be helpful when developing or improving a classification scheme of a mineral group. If you are unfamiliar with site total charge arrangement or root charge arrangement concepts, please see the publication by Bossi et al. After the database is generated, it's stored in the target directory as a HTML file. It's opened automatically using a web browser. Just to assure you, this takes place offline, so no data are uploaded to the internet. The reason for choosing this file type format was that it nicely displays formulae, including scripts and superscripts, and it can be easily opened and edited using text editors such as Microsoft Word, for example. You can open the database directly from the project folder or button in a box display files. At the bottom of the main window, which is the button database in this case. As for the database for the titanium rich garnet from magnet cuff, you can see that 3 distinct site total charge arrangements has been generated with some more subordinate root charge arrangement and charge balance formula. There are 33 potential end member formula in total. At the moment, we want to use a search and match algorithm to evaluate user data and to assign an end member formula to the complex titanium rich garnet composition. The user data are input via an Excel type spreadsheet. We generate the spreadsheet first using the button Excel template. Use Microsoft Excel or a free alternative to open the template. Indeed, two spreadsheets are generated, one of them called template and the other one called nomenclature. The nomenclature function assigns mineral names to the items in the database generated in the previous step. This function is optional, you can skip it, but if you use it, you can assign not only a member formula, but also mineral names to your user data. I demonstrate the nomenclature function first. So make sure the spreadsheet of you handle has a nomenclature in its name. This is how the spreadsheet looks like. Column A guides you on how to fill in the values in the cells. The first cell just informs you that you input your data in atoms per formula units. So you can start inputting values from the column B. So let's define andradite. Write andradite to the first row of the column B. First cell in the second row tells you the name of the first site. So leave this row blank. Fill in only those cells which are relevant. So we need to define that andradite has three divalent calcium atoms at the site X, 2 trivalent iron 3 plus at the site Y, 3 tetravalent silicon cations in the tetrahedral site, and 12 oxygen atoms as anions. Please don't confuse the site name O with the amount of the oxygen 2 minus. You selected the name O for this site. In a similar manner, you can complete the nomenclature relevant for your composition space of interest. So I will add more known garnet species, which I prepared in advance. Don't forget to save the changes in the spreadsheet. Now it's finished and we can close it. Next, select Read Nomenclature. This launches the search and match algorithm for all the entries, including the middle names, and matches them with the database items. This is the report. You can see an n-member formula has been assigned to each entry, and the name was assigned to this formula from the database. There should always be a 100% content of the assigned n-member in the user-defined n-member. If not, it implies a mistake. Also, we can reopen the database and see that the mineral names have been attached to the matched items. Let's move to the input of user compositions. The approach is essentially the same as we have just seen. Open the Excel spreadsheet with the template in its name. This can be done either from the working folder or by selection of a user data input button in the main window. Write the sample name in the first row. Then fill in all the numerical values. Few technical notes here. Please never delete or add rows in the spreadsheet and don't change the order of the rows. You can make changes in the column A, but the content of the other columns must always correspond to the order as generated by the program. There are some rows, such as this one, the sum of the divalent cations in the X site. Generally leave these rows blank. It only makes sense to fill them in if your user data contain minor elements which do not occur in the list of constituents here. Don't forget to save the file once the input is completed. Then select Read Template. After a while, we automatically receive a report with the results of the search and match algorithm. For each sample, which corresponds to each filled column in the template, we get a mineral, formula, check of the charge balance, an overview of the total charges at the sites. What follows are the hierarchical steps of the dominant valency rule approach. The dominant site total charge arrangement, including quantification of its molar fraction, and a detailed explanation of the limiting factors of the assignment. Then the matched root charge arrangement and the matched end member, which is highlighted in blue. This example, garnet, is classified as monoimotoid according to the dominant valency rule. In contrast, the dominant end member in this solid solution is sholomite. The divergence of the two rules is discussed by Bossi et al. Using this garnet example. If you are interested in the calculation procedure in more detail, there is an advanced feature which outputs the calculation results for all considered alternative solutions. Select Detailed Output button. This creates another HTML file. To export these files, appropriate to open it using programs such as Microsoft Excel. What we see is a table similar to the database from the beginning of the tutorial, but including the sub-results of the search and match algorithm for the samples of interest. I recommend using filter function so it's possible to make comparisons, sort the data, and so on. For example, you can display site total change arrangements only by filtering out the empty cells in the column G. If you close your project, you can open it again. Just select Load Project after you launch the program. Then you select the file of the file type .mat with project in its name. There are many more working examples available to explore the program capabilities. The examples mostly originate from the publication by Bossi et al. In Mineralogica magazine, or another one in Minerals. Furthermore, there are several examples of the type or co-type compositions of tourmaline supergroup minerals, most of which were approved relatively recently. You can copy the examples to your projects directory. I will run one of the examples. There are several options allowing for modifications of the default settings. For example, the maximum number of sites where double occupancy can occur can be increased. Although, for most minerals, this would mean a deviation from accepted rules and conventions, an approach discussed by Hodorn 2021 to derive an N-member formula for yttrium-rich hynite can be reproduced if we change the value to 3 sites. I hope this video helps you use the program and that N-member Hunter supports your work. I would be grateful for your feedback and would be happy to meet the community of users. Please be so kind and cite the program if it helps you with your research. Thank you for your interest in N-member Hunter.